Why can't you simply neutralize an acid with a base? Why is it so important to control the acidity of solutions anyway? And how do acid-base buffers know what to do? Keep watching to find out. Many people with a basic or intermediate understanding of chemistry think you can just neutralize some acid with some base, and that's understandable. We've been taught that that's what happens in early chemistry lessons, and probably you've done calculations to work out exactly how much sodium hydroxide you need to neutralize a certain amount of hydrochloric acid. And you might even have done an experiment to neutralize an acid with a base by titration. But those school experiments are fixed. Not in the sense that it's cheating, it's just that either the acid or the base will be weak, the titrating solution fairly dilute, and you're probably not using laboratory grade accuracy. But accurately neutralizing a strong acid with a strong base is so difficult, it's generally just not done. To give you an extreme example, I heard a story from a colleague who'd been supervising undergraduate lab classes where a student had spilt some acid on his hand. Now, I don't know how concentrated it was, but it was enough to do him a minor injury. Probably just a bit of a rash if he'd gone straight to the sink and rinsed his hands in lots of water. But instead, he decided to neutralize the acid by pouring sodium hydroxide on his hand. It left a hole! But why should neutralizing a strong base with a strong acid be so difficult? The reaction equation says it's possible and the calculations say it's possible. So who's wrong? Me or all of the chemistry textbooks? Well, neither of us, obviously, but what many early textbooks won't tell you, or students just miss, is that the practicality of neutralizing solutions is much harder than the theory. So let's take a look. So I'm back in the lab, got my lab coat on, goggles and gloves. I'm gonna take 10 milliliters of 1 molar sodium hydroxide. I'm gonna take 10 milliliters of 1 molar hydrogen chloride, mix them together, they're going to neutralize each other, pH 7, lovely. Now that's actually pretty good. The sodium hydroxide solution has gone from a corrosive 1.0 molar solution to a non-hazardous 0.002 molar solution here, or 500 times more dilute. Or put another way, 0.00 molar sodium hydroxide. For some cases, this would count as neutralizing the hydroxide solution, but for most situations, especially the environment, medicine, or research, pH 11 is still a long way from being neutral. And that's because we have to consider unimaginably tiny volumes of H plus or hydroxide. And that's important because protons and hydroxides are indiscriminate catalysts, and we only need a tiny amount of them to do a lot of damage. Now let's get back to the lab. Okay, so that's a fair way off of being neutral. So that's come from the inaccuracies in the grading on the glassware. So let's just add a few drops and see how it goes. I'm going to spare you that and we'll go straight for neutral. So that's pretty good. I got to 7.7 with my first effort plus 3 drops of 1 molar hydrochloric acid, which actually was better than I was expecting, especially given that the grading on this equipment is fairly rough. So well done me, but we're not there yet. I want to get to 7.0. In many chemical applications, we need accuracy to at least 0.1. So let's add 1 more drop. Whoops. We've gone too far now, so let's try 1 drop going back the other way, 1 more drop of sodium hydroxide, try and get us back up to that 7.0, and I'm going to use a slightly smaller pipette to maybe get a smaller drop. Let's see how that works. So that's better, but I've still got a long way to go if I want to hit 7.0, and it's late and it's time for me to go home now. Before I get into it, we need to set some terms and conditions. First up, we're using the Bronsted-Lowry theory of acids and bases today. I've made a video all about that, so check it out later if you haven't already. That means we're going to measure the acidity of a solution by the concentration of positive hydrogen ions, H+. And I'm going to be calling positive hydrogen ions protons in this video because that's what a positive hydrogen ion is. Now, you probably know the pH of neutral water is 7, exactly 7. Here's the equation for calculating pH, and if we rearrange that, we can see that the concentration of H+ in neutral water is about 1/10,000,000th of a molar. In other words, pH 7 means an unimaginably tiny concentration of H+, and that means you only need an unimaginably tiny amount of hydrochloric acid to make the water more acidic than neutral. In fact, if we had 1 litre of pure water, only 90 millionths of a mole of hydrochloric acid would reduce the pH to 6, which is slightly acidic. And going the other way, if we wanted to remove enough protons to neutralise 1 litre of a solution at exactly pH 6, we'd have to add just 90 millionths of a mole of sodium hydroxide to get the pH back up to pH 7. So let's see how that's going to work out. Let's suppose that we want to neutralise it with a solution of concentrated 10 molar sodium hydroxide. That's how it comes out the bottle here. How much of that do we need? 0.000009 litres, or 0.0009 millilitres. Okay, well, how hard can that be? Very hard. Roughly speaking, the size of the smallest drop of water we can get from a pipette is set by the physical properties of water, in particular surface tension. The high surface tension of water means that a drop can get quite large before it falls off a nozzle. For a simple glass pipette, the smallest drop you can get is about 0.05 millilitres. So every drop of 10 molar sodium hydroxide will contain 0.00005 moles, which is about 55 times too many. And this single drop would take us straight past pH 7 and nearly up to pH 10. Whoops. So we could dilute the concentrated hydroxide accurately 55 times to use a single drop, or less accurately by about 500 times to use about 10 drops. Or we could use an expensive micropipette to reduce the size of the sodium hydroxide drop in the first place, or a combination of all of these. But none of this is just neutralizing some acid with some base, is it? And it's certainly too complicated and expensive for most cases where we want to get an exact pH. And that's a big problem by itself. But it's not even the biggest one. You see, this box contains laboratory grade pure water, over 99% pure. So, pH 7, right? Well, let's find out. I'm going to use a pH meter, and maybe it'll sit around on the bench for 10 minutes or so while I get things set up. And so here we go. Pure water, pH 7. Oh dear. So what's gone wrong? Well, as anyone that works with water chemistry will know, it's carbon dioxide. And guess what? The air's full of it. So if I let the water stand in the open air, the pH will steadily decrease to below 6. In fact, I can take the water up to pH 7 again simply by bubbling it with nitrogen. The carbonic acid will turn back into carbon dioxide, which will evaporate into the nitrogen bubbles and thereby reduce the acidity of the water. It takes about 15 minutes, but here we are, back at pH 7. But the problems don't finish there anyway, because we haven't talked about stability yet. Because unless you're going to work in a glove box, that pH 7 water will not stay pH 7 for long. Within about 20 minutes, that pH will be back under 6, and that's assuming there's no chemistry going on. And carbon dioxide is just one possible contaminant. In common water-based mixtures like food, drinks, gardens, bodies, we also have to deal with oxidizing organic compounds turning into acids, oxidizing metals turning into alkalis, and ingredients or impurities bringing their own acidity and alkalinity. You can see what we're up against. But controlling acidity in aqueous solutions is crucial. Some molecules need to be fully protonated, meaning we need a low pH, while others need to be fully deprotonated, meaning we need a high pH. And others, especially biological molecules, need to be partially protonated to precisely the right degree. That means we need precise control over biochemistry in the lab, in hospitals for storing blood, in our bodies for proper lung function, kidney function, and protein synthesis, for gardening and farming to give plants the right conditions for their roots, and they all need different acidities. For fish keeping to keep their water at the right acidity for their bodies, and different fish need different acidities. In cooking to get the correct taste and to catalyze the reactions we want. In the sea to make sure corals can grow and plankton can grow to feed everything else, including us. In short, any situation where there is chemistry in water. But I've just shown you how difficult it is to get the right pH. Whoops. So what do you do when you have to keep the pH stable within a certain range? We use a buffer. Bet you didn't see that coming. A buffer is a mixture of a weak acid and a weak base that keeps the pH in roughly the same place by releasing and taking up protons. If we go back to the lab and test the pH of this buffer solution, we can see it's stable at 6.86. But how do they work? And how do they know when to release or take up protons? And how do they know how much? They don't. Let's take a closer look. As I said before, a buffer is typically made from a mixture of a weak acid and a weak base. And if you don't know about conjugate acids and bases, it's all in that How Acids and Bases Really Work video. Now, the practical details of choosing buffer mixtures and making them up are quite complex, so I'm going to keep things really simple here. The buffer acid and base have to be weak because they need to be in the same mixture, and we need them both to be working. And if we mix a strong acid with a strong base, they'll just react together and we end up with the same problems that we discussed earlier. Now, the practicality of which acid and base to use for the buffer depends on a number of factors. Most importantly, which pH range you want to be working in and how accurate it needs to be. Then you have to be sure that the buffer is chemically compatible with all the other chemicals in your solution. In other words, it won't start reacting with something it's not supposed to be. So when scientists are making up their buffer mixtures, they'll first choose their acid-base system, for example, citrates or phosphates, or even citrates and phosphates. Then within that system, they'll adjust the ratios of the buffer acid and buffer base to get the exact starting value of pH that they want. And if we're careful, we can balance that pH to 2 significant figures if necessary. And there are simple lists that will tell you which kind of buffer mixture to use and the proportions for the pH you want. For now, however, let's take a look at this really simple model. On the left, we've got the buffer acid with its hydrogen atom ready to drop off and become a hydrogen ion. On the right, we've got the conjugate base of the acid, which is going to be our buffer base, and it's got a negative charge because it's lost the proton. Now, if we add some extra acid from outside, that's going to increase the concentration of protons floating around in solution. Very simply, the protons in solution will react with the buffer base molecules, which will remove the protons. Or we can go the other way and add some base. In water, that base will increase the concentration of hydroxide ions, and they will react with the protons from the buffer acid to make water and get neutralized. So you can see that the buffer mixture is a way of adding lots of acid and lots of base to a mixture, so that either one of them can take excessive acids and bases out of solution. In this super simple model, the buffer is used up when it runs out of either acid or base. We then say it's saturated and the pH starts changing quickly. This is why chemists will choose a buffer that starts close to the pH range they expect to be working with. That's because a pH change of 2 means a change in concentration of 100 times. So that's the most simple explanation. And frankly, it's good enough for most people that need to use buffers. But if you're watching a 326 video, you'll be a smart cookie. And you might have realized two things. Firstly, there's a big problem with the simple model of how buffers work. And secondly, you haven't clicked the like button yet. See what I did there? Thank you very much. Now, back to that problem I mentioned. I said the exact pH depends on the ratio of the buffer mixture. They'll adjust the ratios of the buffer acid and buffer base to get the exact starting value of pH that they want. But in our simple model here, the ratio changes quickly as we add extra acid or base. That will make one side much stronger than the other, meaning the pH will also change quickly. Not as quickly as having no buffer, but still too fast to keep a pH stable for hours. That might not be a problem for simple applications like gardening, but it would be a big problem for scientific or biological applications. So let's take a closer look. You see, buffers have another very useful property. Whenever the acid and base get unbalanced, they'll swap protons until they get the balance back. But how do they know they're out of balance? And how do they know how many protons to swap and which way to send them? They don't. Very simply, the buffer molecules just keep on doing what they've always been doing. Each acid molecule keeps releasing protons into the solution at the same rate it always was, and each base molecule keeps taking them out at the same rate it always was. But together, they make something called a dynamic equilibrium. If you don't know how a dynamic equilibrium works, I really recommend this video where I make a dynamic equilibrium using only some dice and some counters. I think it's one of my best videos and it hasn't had the love it deserves, so be sure to check it out if you haven't already. But for now, let's get back to our simple buffer model and add the dynamic equilibrium by moving the model forwards in steps of time.
Steps of time.
I should totally write that movie. In each time step, each acid molecule will have a certain probability of releasing a proton, and each base molecule will have a chance of picking up a proton, if there's one available. And let's start by making the two probabilities the same at 25%. What I'm doing here is using the random number function on my calculator to generate a random number. If the first two digits after the decimal point are 25 or under, I will ionize the acid or protonate the base if there's a proton available. And I'm going to do that for each molecule. And when I've done all 12, that's the end of one turn, and I go on to the next turn. It takes about 2 steps for our system to reach equilibrium, and the first thing you can see is that the acid and base molecules are continually shuffling across to the other side and back again. If we stop and look at the number of protons in solution, you can see that the numbers go up and down a little, but we mostly see about 2 protons in solution. To understand how the dynamic equilibrium works, let's take a look at the 2 extreme cases. When there are no protons in solution, there's only one way for the system to move. There are no protons for the bases to take, and some of the acids will release protons. So the number of protons must go up. But when there are lots of protons, in this case 4, we see the real strength of a dynamic equilibrium. Firstly, there are 4 protons now, so there are protons available when a base gets its 25% or under. But also, there are far more base molecules than acid molecules. So the base side has more chances to pick up a proton every turn. These two things together mean it is much more likely for the number of protons to decrease now than increase. This dynamic equilibrium is how the buffer acid and base shuffle protons between themselves and always end up with roughly the same proportions of acid, base, and protons in solution. With this tiny model of only 12 molecules, the numbers do fluctuate between 0 and 4, but the relative size of that fluctuation gets much smaller as we add more molecules. In the dynamic equilibrium video, I use a simulation to show what happens with 1,000,000 molecules. And we can't see it at all in normal laboratory amounts of zillions of molecules. All we can see is the pH holding steady to 2 significant figures. But our simple model can also simulate different buffer mixtures. Our equal probability model has an average of 1.7 protons. But if we make the acid twice as likely to release protons than the base is to retrieve them, the average goes up to 2.0 protons. And if we make the base twice as likely to receive protons than the acid is to release them, they go down to only 0.7. The equal probability model is behaving like a neutral phosphate buffer, the high acid probability model like a citric acid buffer, and the high base probability model is like an ammonia buffer. And we can also see how buffers absorb added protons and hydroxide ions. Now, we could add hydroxides explicitly in our model and do all the same calculations, including them, but we don't actually need to, because hydroxides just react with protons to make water, and they both just disappear. So we can get the same effect of adding hydroxides simply by starting with fewer protons. Now, a quick aside for those of you that know the difference. For detailed simulations, we'd have to include water dissociation, but we're keeping things simple here. And for those of you that don't know what water autodissociation is, don't worry about it for now. So if we added an extra 2 protons to a normal non-buffered mixture, of course the number of protons would just go up by 2. But in a buffer, the base is ready to pick them up, and the protons then get shuffled between the buffer base and buffer acid to keep the two sides balanced. So even after adding an extra 2 protons in our simple model, the average number of protons in solution only increases from 1.7 to 1.9. And if we remove 2 protons from the first model, because the buffer behaves as a dynamic equilibrium, the number of protons in our buffered solution only goes down from 1.7 to 0.8. So there you go. That is how buffers work to resist changes in pH. Nothing needs to know or care what it is doing. Everything just keeps doing what it was doing all along, with the acids releasing protons, the bases taking them up again, and statistics doing the rest. Now, I deliberately kept this model as simple as possible, but there are many ways it could be improved or developed. For example, at neutral pHs, the autodissociation of water, where water spontaneously breaks up into H3O plus and OH minus, becomes significant. How would you add that in? You might have some other ideas for a model like this, so be sure to put them in the comments. I'd love to hear them. Now, this simple model was cool, but let's finish up by putting this all together with a much better animation. But before I get to that, I just want to say this video is produced at Kyushu University. It's one of Japan's top universities, and we have a range of courses in science and engineering in English. A great alternative in these uncertain times. So check out the link in the description. And now, let's take a more realistic look at how buffers work. Here we can see a phosphate buffer, with phosphate as the buffer base and hydrogen phosphate as the buffer acid. And these molecules are separated by water molecules. And you already know from the simple model that any additional protons will get picked up by the phosphate bases, or any additional bases will get neutralized by protons released from the hydrogen phosphate acid. This animation is so cool, and I want to say thank you to my YouTube members and Patreon supporters for enabling me to bring this to you. So, there you go. Now you know why you can't simply neutralize a strong acid with a strong base, what a buffer is and why we need a buffer to control pH, and you know exactly how a buffer works. If you'd like to help me get videos out more often, you can join our supporters by clicking the join button below or by joining the 326 Patreon. There's a link in the description. And just quickly, if you haven't seen my dynamic equilibrium video, you can check it out here. It really shows you how dynamic equilibria automatically adjust themselves to get back to equilibrium. And this video is great too. And I'll see you next time.